last part. Actually, I was kind of worried that it was going to go too long. So I apologize for leaving that out. This shouldn't take that long. Just as a preface, if you aren't a computer engineer, don't care about hardware, don't listen to this thing. It's pretty complicated. There's a lot going on here. So don't worry if you feel like there's just too much. But in any case, let's spend a little time on hardware. And I think the best way to understand this is, well, all this stuff has to run on something, doesn't it? What do you think? So I think the main thing to understand is that there are actually two sides to everything. Now, computers, in the end, I'm going to do a 2-slide computer engineering course. So I apologize to all the real computer engineers here, but I think this gives you a little intuition. And the first is that there are really two kinds of software code that you run. The first is what you might want to call control. This is actually what's running right now. It's very irregular. You do a little code, then you branch, and you can have billions of branches per second. So this slide just has a little piece of pseudocode that says, while things are true, you want to input an app name, so you're getting a name from the user. If you don't have that much memory, then you want to run the app right in memory. If you have a lot of memory, then you want to run it as a subprocess. What you notice about this is there are a lot of steps that they're not very long, right? So you're going to go down here, you're going to get some input, then you do a branch, and then you do this. Otherwise, you do the other thing. It's really hard to make all this code work. It's something called branch prediction, but you have to sort of predict which way the code is going to go. And so traditional CPUs like the Intel processors or the M1 Mac Silicon is really tuned for this. Lots of little pieces of code running very quickly, but they're always changing. And what happens is if you don't do this right, these computers end up stalling. They're just waiting to hear from you. And they do things like speculative execution, which basically means it guesses based on, well, last time there was limited memory, so I think I'm just going to try to run down this branch. If it turns out there's not, then I'm going to have to stop the pipeline, and I'm going to run this branch. Now, the interesting thing is that large language models are sort of the reverse. They're basically long runs of doing the same things over and over. As we said in the previous things, it's all about matrix math. A equals B times C, where A is a matrix and B is a matrix and C is a matrix. And it's very regular. In fact, there's almost no branching. The code down below says for I, which is the first index, from 1 to 50,000, and then for J, from 1 to 10,000, and then for K, for 1 to 2,000, set A sub ij is equal to B ik times C kj. This is called a dot product. And actually, this loop is going to run 10 trillion times. So what you notice about math is it's very regular. There's very little branching. And there's what's called parallelism here, which is to say you can actually calculate I and aij for each independent one without any dependence on the other things. So totally different. And it turns out two big branches of computing have emerged to take care of these two very different problems. This is the point where I normally say, hey, Dion, do you have any questions? So I'll just say, hey, Dion, I hope you don't have any questions. Now, this is a bit of an eye chart, but when you understand that everything's about keeping the processor filled up, you'll see that the important thing is caching and pipelines. And the main thing to understand is the world is very, very slow compared to what a processor does. Just this eye chart shows you, I just took a typical CPU like a Skylake processor. You might have one. And what it says is the processor is actually running at 4.3 gigahertz, 4,300 gigahertz. And it basically runs every 0.23 nanoseconds. It's kind of hard to imagine anything running that fast. There is a cache, which is basically trying desperately to have all the instructions and data the CPU needs. And it's about, this is a little bit of a thing, it's 32K bytes. That's kilobytes, not very much. But it runs at 1,000 megahertz and has a latency of 1 nanosecond. So that means that it really is pretty good at keeping up. It has a system bandwidth of about 1 terabyte per second. So basically, if a CPU needs data, it takes about 4 ticks for it to hit the level 1 cache. And the whole goal is to keep the processor busy and running at 4.3 gigahertz. Because if it doesn't have the right data, it's just going to slow down and do nothing. So who cares if it's running at 4.3 gigahertz doing nothing. Now, the interesting thing is these systems have multiple caches. After the level 1 cache, there's a level 2 cache that's a massive 100 megabytes. It runs at a slightly slower clock rate. Its latency is 4 nanoseconds. By the way, 4 nanoseconds doesn't sound like very much, but compared to 0.23 nanoseconds, that basically means that if you do a level 1 cache miss and you get to level 2, the processor is going to be waiting for, wait for it, right? Tick, 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 20 cycles, just sitting there doing nothing. Now, there's another cache that's a level 3 cache that has 110 megabytes. By the way, if you're wondering why these caches are so small, building these things is very expensive to make them run at 1 nanosecond. So these things are gigantic. They use what's called static RAM. They're super performant, but they're very expensive and big on the chips. So they can't have that much space in them. Now, the level 3 cache runs at 19 nanoseconds. It runs at 400 gigabytes per second, and you can see this ratio is basically 10x. So if you miss in 1 and miss in 2 and you're in 3, you're at 19 nanoseconds. You're really slow. But here's the good or bad news. The next stage is something called dynamic RAM. This is the little chippies that you buy when you say I want 512 gigabytes, and typically there's 8 of them. Now here's the good or bad news. These things run at 93 nanoseconds. So look at the difference between 0.23 and 93. This thing is waiting a long time. And the bandwidth is much slower too. You get about 400 gigabytes per second. So feeding this thing, once you get started, it's not bad, but you don't want to be way out there. And DDR4, which is an older RAM, actually has some different characteristics. But one thing is that sometimes things get slower and faster. So as an example, this particular example, the DDR RAM is actually 68 nanoseconds, so quite a bit faster, but sort of doesn't matter. So one of the ways to think about this is if you were a Skylake processor and you did a new thing every minute, like I'm looking at a piece of paper every minute, I'm trying to do something new. The way to think about that is just to get to RAM would take about 5 hours. So if you suddenly had to go RAM, like into the closet, you'd have to rummage around there for 5 hours before you could do useful work again. That's the difference between 68 nanoseconds and 0.23 nanoseconds. Now, the funny thing is that GPUs are actually quite different in terms of their loading. This is an H100. This is the standard NVIDIA GPU. First thing you notice is the clock rate is much, much slower. It's running at 1.75 gigahertz. And that means its latency is about 0.57. So it's actually running 3 or 4 times slower than a Skylake GPU. And now you say, why is that? Well, you'll see in a second. That's because it's got a lot more of them. You can sort of think of Skylake as Mr. Speedy Gonzalez running around. The GPU is more like a slow marching army. Clunk, clunk, clunk. If you ever watch Lord of the Rings and you see those armies, that's what it's like. Now, the interesting thing is its first level is something called shared memory, and it's a little complicated, but basically it has 256 megabytes of that. It's got a clock frequency of 1.5 gigahertz, and you notice it actually runs much slower at 16 nanoseconds. So what you're going to see with GPUs is they run much slower, but they have much more bandwidth. The level 1 cache is 256 gigabytes, and you see it runs actually very slow, 150 nanoseconds. That's a whopping 300 times slower than the GPU. So if you have a stall in level 1, you really got a problem. There's a level 2 cache that's about 50 megabytes, it's about 50 megabytes, that's correct. And it's even slower, 234 nanoseconds. So it's a huge percentage slower. But look at the bandwidth. The bandwidth here is 2.8 terabytes per second, and the overall system is 5.5 terabytes. So compared to a CPU, it's pushing so much more data. It's pushing 5 times the amount of data into these GPUs. And that's because it can become slower. It's like a gigantic army that's eating a lot of food. Now, there's something called HBM, which I'm going to talk about a little bit more, called high bandwidth memory. This stuff is super, super expensive. 160 gigabytes of this stuff literally costs $20,000 or $30,000. But the interesting thing is it's got a somewhat lower latency and it's got a lower bandwidth, but the overall system bandwidth is unbelievable at 2 terabytes per second against, I'm on the wrong line. its bandwidth is about 380, but its overall system throughput is almost 2 terabytes per second. So look, compare that to a DRAM, which is running at essentially nearly 5 times slower. And you can see why there's so much attention to these HBM memory. But even then, compared to what you get in level 1 or level 2 cache, there's no doubt that you want as much stuff stuffed into these caches as possible. A lot of the attention mechanisms and other things we talked about are all about just making sure things are in the right place. Now, the other things are VRAM, which is an older technology that's used in the consumer systems. This is much less expensive than high bandwidth memory, but it's somewhat slower. And then typically, one of the things about GPUs is they can't store everything in this HBM, so they have backing DRAM. And what it means is that when you want to get something from DRAM into GPUs, you actually have to do a full copy from here to here. So you got to copy terabytes of data from DRAM to HBM. Don't care how fast it is, it's going to take a long time. Last thing we'll talk about is something called NVLink. This is the thing that connects GPUs together. So if there's, for instance, some weights or some information in one GPU's memory, say way over here, number 2, and it's number 3, you got to go call and get it. And that takes a whopping, sorry about that. I always hate it when I hit my mouse too fast. That takes a whopping 2.3 microseconds, which seems not that slow, but compared to 0.54, it's literally like 4,000 times slower. So you don't want to go over there. Now, I say all that, but if you're all the way out on disk, things get really worse. So NVMe, which is a kind of SSD, you can store 16 terabytes, which is quite a lot, but it takes about 20 microseconds to access. Just think about that, 20 microseconds versus 0.223. This is literally like 10 to 20, 100 times slower, and the bandwidths are much slower. A serial ATA SSD array, which I think is super fast, well, it is sort of fast, except latency is like 2 milliseconds, which is 2 million times. So that thing is literally 5 million times slower than a Skylake processor, which is why we have all these hierarchies. And the bandwidth is much lower. If you have to go over the internet, even the very fast 10 gigabit Ethernets take about 30 microseconds, which is much, much slower than all of these numbers. And then if you have to go to a hard disk array, I have bad news. That's about 20 milliseconds. That's about 40 million times slower than a CPU. Now, put another way, if this Skylake processor we talked about has to go over the Ethernet, it's going to take about 2 years for it to get some data from over the 10 gigabit Ethernet. Think about that. You've got a 1 minute thing to do. You got to wait 2 years for the next piece of data. Now you can see why caching is so important. By the way, just to continue the analogy, if you do misses everywhere and you have to actually go to the hard disk and wait, that's about 165 years equivalent that you'd have to wait with a Skylake GPU. So essentially, if you have to go to disk, you are done with most of these systems. So it's all about caching and filling the pipelines. Now, as we said before, the GPU is actually much slower, but it handles 5 times the volume. And that's because bandwidth is king for GPUs, because it's doing, the 10 million things over and over and over again. And so it doesn't have a lot of these problems with, oh, I need to go over here, I need to go over here, I need to go over here. One of the ways to think about it is bandwidth is king for GPUs, whereas latency is king for CPUs. And that's why you don't really see CPUs doing a GPU's job or vice versa. Well, computer engineering in 2 slides. What do you think? All right, let's go on to how these things actually work in practice. Now, one of the ways to look at this is an example of an Intel Cascade Lake processor. And I know it's an eye chart, but one of the ways to look at it is it's pretty complicated, okay? So you see that there's this thing called a level 1 instruction cache. This thing is spending all its time trying to figure out where I'm going to go. Remember I had that if statement? It actually does what's called branch prediction, just trying to figure out what's going to happen next. And down here is a data cache. So there's literally half the chip is devoted to predicting what's going to be next, filling the pipelines, figuring out what's going to happen. And then the actual execution happens down here. And there are these, 8 execution units that are running simultaneously. So this thing basically comes up here, tries to figure out what instructions to run, looks for parallelism. So it tries to find things where you can run 8 different things simultaneously, and then tries to fill the pipeline down below. And it's very well tuned for things like Linux. And that's why you see that when they scale this, you don't have that many, you have a lot of processors here and they're all identical. So this is an example of a 28 core system, and it's this little building block repeated over and over and over and over again. 28 of these units just trying to predict branches. Things like Linux or Mac or OS, there's hundreds of threads. If you ever turn up the activity monitor or the system monitor inside these systems, you see like hundreds of things. Like right now, I probably have OBS Studio running. I've got Brave running. It's checking the hard disk. All these things are doing very different, disparate things. And what's happening is Intel's just trying to jam out all that stuff in there and have it run efficiently. Now in AI, what happens is things like these CPU boards are what loads up the data. And the cost is about $2,000 a board. By the way, that's 20 times less than a GPU. And if you look at their ability to just do multiplies, like a GPU, it's about 1 to 2 teraflops, which sounds like an awful lot. And actually, until GPUs arrived, was an awful lot, but it's not really tuned for that usage. So that's why you see people spending a lot of time saying, well, what is my CPU doing? But really, I want to talk about what the GPU is doing. Okay, let's look at a GPU. Well, GPUs are kind of an interesting thing. You probably have heard of NVidia. Kind of remarkable how important GPUs are. In fact, this chart was actually taken back in February. The number's a little higher now. But NVIDIA, which just makes GPUs, has become literally the king of the stock market. So on the left here, you see the market cap history of NVIDIA from 2001 to 2024. You can see it had a little, basically nothing happened. It had a nice bump, but my God, look what happened here. So it did have a little bump, but in the last year, it's just gone crazy. In fact, today, if you take a look at all the most valuable companies in the entire world, and this varies a lot, obviously. You see Microsoft at 3 trillion, Apple at 2.8 trillion, Saudi Aramco at 2, Google and Alphabet and NVIDIA are just competing in this. In fact, NVIDIA, the latest data just passed them. So Google, which has been around for a long time doing search, and Amazon, which has been a long time around doing shopping, is not as valuable as a company making GPUs. Think about that for a second. And the question is why? What's going on? So the intuition here is the GPUs have become the darling and the only way to process AI models. Now, if you want to look at the difference, GPUs are in essence 1,000 times faster doing matrix math than the equivalent regular processor. 1,000 times. That means if you had a job that would take 1 day with a GPU, it would take 1,000 days, 3 years with a CPU. And that's why there's so much focus on it. Now, how does it do it? The answer is something called a streaming multiprocessor. A typical GPU in an H100 has 148 of these things, versus say 24 with Intel. And it's got a very, very regular structure. This is an eye chart, but the thing on the right is actually 148, all 8 of these things all duplicated in a single chip. And you can see they're much smaller modules because they're not doing as much. And the trick is they do what simple linear instructions where they basically do the same math across 32 different things. And when you saw the multiply example, remember when you multiply those things together, A equals B times C. None of those are dependent on each other. So I can split those trillion calculations up across 148 symmetric multiprocessor units. I have no need to do instruction prediction, and I'm just going to be 148 times faster. Now this board costs $30,000, and the key is the simple unit. It's called single instruction multi-threaded is very simple, and this is what it does. There's an instruction cache. There's a scheduler, which says it can process 32 things at a time, and it dispatches 32 things. It's got a little bit of RAM, and then it's just got execution units. So it's got 16 execution units for 32-bit integers, 32 32-bit, and 16 64-bit. So when this thing comes in, it's got 64 bits. It just says, okay, I'm just going to load you up, baby. Or if you're doing integers, I'm going to load you up. Floating point 32 is a very popular format for large language models, and it can run 64 of these things at once. Think about how fast that is. There's also something called a tensor core, which is even more acceleration. This is specifically to do matrix math. And that is how they get this 1000x speed up and why NVIDIA is worth so much money. just to give you a little more intuition here. Remember I told you these workloads are identical? Eventually, even one of those boards isn't going to be fast enough. So NVIDIA and others went through a lot of work to connect multiple processors together. Now, why is that important? It's because, remember I said this one matrix, you can multiply anything by anything. So I can share it across those 148 SMs. I can also share it all the way across GPUs. So because the heart of AI is about matrix multiplying, there's three very hard problems. The first is fitting this like 1 trillion, some of these models are a billion parameters. A billion times 30 times 64 is a huge amount. You need 4 gigabytes of RAM just to hold one matrix. And it's very expensive and very hard to fit all that in. Even with 160 gigabyte HBE RAM, you can actually run out very quickly. And the second, as we talked about, is the overhead of finding things on disk, moving it to DRAM, which is what the CPU does, and then copying it to HBRAM. So once you get this thing set up, it takes a long time to get it set up because the CPU's got to shovel, find on disk where all these things are. The GPUs are not generally connected to disk. They just have HBRAM, and the CPU loads it up, and then the CPU says go, and then the GPUs go. So the CPU is sort of like the slow, I always think of it as like the slow cowboy running around doing its thing, and the GPUs are like the thundering herd that are going to do all the work. Now, the most important thing to notice is that this global memory, this connection is very, very important. It has to be very, 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 very fast. And this is where NVIDIA has really innovated to make that connection as fast as possible. So if you have 8 GPUs, it's nearly as fast as a single GPU. If you want to lash up 128 GPUs, you can do the same thing. And they've invented something called NVLink, which we'll talk about in a second. There's super fast ways to connect all this shared memory together. So let's talk about how it all works. This is a toy that I think everyone who wants to do home computing should get. This, by the way, little baby cost, I don't know, between $250,000 just to get the hardware. So this single module has has 8 full GPUs combined all on a single board. So there's 8 H100s, all with 160 gigabytes of memory on this thing. And then there's something called NVSwitch, which uses NVLink. It's got 4 NVLink connections. So this GPU can run around over here, and if the weights are over here in this machines, it can find it. This guy's doing the same thing. Oh, I need some weights from over this guy. I'm just going to go get it. So this kind of latency, and it's a miracle that this stuff can happen in microseconds. And so the shared memory idea is very, very important. Just to give you an idea of some of the expense. So it's not just the GPU, it's all the stuff put together. We don't have time to cover it, but HBM, which is high bandwidth memory, is actually gigantic modules of RAM just all stacked together, right? So you can't even put it on standard PCB. So the engineering that goes into this design is incredible. And in fact, NVIDIA provides a reference design, which is what this is, that other people can then go build. And the interesting thing is this typical rack costs about $250,000. It's got 8 H100s in it. Now, if you want 1,000 of these things, can you just imagine the amount of hardware it takes to, this is one board. You got 8 more of these boards all connected together. You got to have switches for those. So it's actually the H100s are the smallest part of the cost. In fact, one of the rough ways to think about it is that it's roughly about $1 billion that you've got to pay for to build a single data center with 1,000 H100s. Let me just repeat that. It's about $1 million per GPU for all of the other junk just to keep one GPU occupied. So if you want to go train a model, it typically takes 1,000 to 8,000 of these things. You've got to find someone who's invested $1 to $8 billion in capital so you can run your models. Now, the intuition here is you don't really want to do this a lot, and only a small number of companies are going to be able to afford it. Tough to go to a venture capitalist and say, please give me $1 billion. I don't know if I'm going to do anything, and I need that money so I can build a data center. But in fact, many companies have already done this, and that is what venture capital money is being used for. Okay, last thing is right here. I just want to cover a very different approach to this. So you can think of those machines we've seen before as super power hungry. In NVidia H100 array, literally terawatts of power being used. A typical Intel desktop machine, if you've got one of these gaming machines like I do, you can easily have a system that needs 1 to 2 kilowatts of power. In fact, the machine I have uses 1.6 kilowatts of power. It's got 2 GPUs in it. Each one burns 400 watts. Kind of amazing, right? Well, Apple did something very different. So what you see here is the Apple M1 Max chip. The current M3 Max is very similar. And what you notice here is all of that stuff, all of that graphics processors, all the CPU stuff is actually on one single integrated circuit. So in the center is the GPUs. In the top is the CPU, and there's actually 2 sets. These are high performance, and then these are low performance. And then all the memory, 128 gigabytes of memory, is in these tiny little blocks over here. Now, why is that important? Well, what it means is that instead of burning 800 watts, this little chip burns about 20 watts. That is an amazing achievement to have something this performant. And the punchline is, remember I showed you all those charts about bandwidth and memory? Something supplying 400 gigabytes per second to RAM requires all that H100 engineering. Apple has accomplished this on a single chip. Right? Now, a typical discrete CPU system, as we talked about, typically when you're really running something, you've got 64 gigabytes of DRAM. In a consumer machine, you have 24 gigabytes of VRAM. And what you have to do, and you've got 48 megabytes of static RAM, and you've got to move all that stuff around. So when you want to load something up, you've got to move it from disk to DRAM. Then you can store a 24 gigabyte model. By the way, 24 gigabytes is not a lot. That's a tiny model. And then when you're done, you got to shift it all over again. So what Apple's done is they put this all in a single chip. And this is what's called unified memory. So the CPU can move things off onto this from the disk, which is very fast, running about 3 to 7 gigabytes per second, stuff it inside this memory, and then just send a note. And there's no copying at all. It just tells these GPUs to get going. So that saves a lot of bandwidth. And then, because these things are tied against directly a 400 gigabit byte per second thing, it runs very fast. In fact, the latest M3 Max with the latest tuning and optimization is roughly competitive to that 800 watt thing with the 24 gigabyte RTX 4090 in terms of speed and performance for inference. Now, this is not going to work for what is called training, where you need a lot of data. But when you're doing inference, the amount of the model really shrinks and you don't have to do as much. So this basically means inference on an M1 Mac and soon Apple Silicon inside iPhones is a real reality. So we're going to see more and more of a split between CPU intensive things, GPU intensive things, and things that are doing inference on the desktop and mobile systems. Okay, well, I just want to summarize the whole thing with one last comment. I know that was a lot to go through, and I apologize to all the real computer engineers, but I just wanted to give you a little intuition here. By the way, I am running an M1 Max right now, and it's kind of ironic. I'm basically using these 2 efficiency cores for 90% of my work. So all this stuff is totally useless when you're using Brave or Chrome as a browser. Just this little tiny thing running a tiny bit of memory, and it's just waiting for the time I'm using Open Broadcast Studio or doing inference to use all the rest of this stuff. So how would I summarize? This is an amazing time that we're living in. You know, the truth is, what I learned in 1983 still mainly applies today. You know, all the computer engineering stuff, all the stuff on programming. Yes, the models have the languages have changed from C to Swift or TypeScript. The computers have changed from a 8088 or a Motorola 68000 to a gigantic M1 Mac. But you could use the same understanding back then to understand computers now. But what I learned about AI in 2019 is almost completely obsolete. And in fact, most of the interesting stuff is less than 90 days old. So we're really at the beginning of a real steep revolution. Now, it won't continue forever, but I hope that you've enjoyed this session. I hope that you've learned a little bit. feel free to reach out to me or Paul or Dion if you have any questions. We just want to share this because it's one of the most amazing revolutions that's happening in our time today. Thanks very much. Bye. See ya.